Okay, it's time to start Chapter 10, Moment of Inertia. This chapter has two sections, which we'll be talking about in a moment. But the second part, which is the part we're going to care about the most, why do we care about this? Well, it comes down to these equations. Okay, you've seen this before. The sum of all forces equals ma. It's Newton's law. You're quite used to that. And if you look at the mass here, what does it do? If you have, for a given set of forces, you sum them up and let them just be whatever that works out to be. What does that cause on this side? The bigger the mass, the less linear acceleration you will get. So what mass is a physical concept. It's resistance to linear acceleration. It's more mass makes it harder to accelerate along a given line. That's what it's doing. Mass moment of inertia is basically rotational mass. So you have a bunch of torques trying to spin something around a given axis. The more mass moment of inertia you have, the more resistance you have to angular motion, okay, and hence angular acceleration. All right? So these are the concepts, and we'll get to that more in due course. Now, I said there's two parts of this. The first part we're going to consider is area moment of inertia. All right? Why do we care about that? Okay, this course is not just concerned about dynamics. We also provide a service for future mechanical engineering courses. And so the concept of moment of inertia for area, all right, so we're doing moment of inertia for mass and moment of inertia for area. This is changing one word. Where does that come up? Well, it relates to shear, and it's relevant to structural mechanics, strength of materials, and fluid mechanics, things you're going to be having in the not too distant future. And because the computation of this is very similar to moment of inertia for mass, or mass moment of inertia, we cover it here. All right? A lot of similarities. So how do we compute this? Let's bring this up. And, oops. So consider the xy plane, and I have a blob of given area. We don't care about mass here, given area. So like a cross-sectional area we're looking at. With a differential area within this blob, and that differential area will be a distance y off the x-axis and a distance x off the y-axis. Okay? And we'll just comment now that it should stand to reason, as here's this blob it's off of both of these axes. If we were to think in terms of mass moment of inertia, which is concerned with rotation, just think about this thing. As this mass gets further off this axis, and if we wanted to spin it around the y-axis, as it were, the farther the mass is away from that axis, or the farther the area is away from that axis, the more resistance to spinning it will have. Okay, and I'll just comment, you see this all the time when you think of figure skaters. So you'll see they skate around and they'll start going into a spin, and they tend to often start with their arms really far apart. And then what they'll do is they'll bring their arms in close. And what happens? When they have mass farther away from the axis of spinning, they spin more slowly. As they bring all the mass in as close as possible to the axis of rotation, they speed up. Their resistance to rotation goes down. All right. So it stands to reason if moment of inertia for areas works like mass, as the area gets farther off the relevant axes, you will have greater area moment of inertia. So how do we compute this? Well, here's the basic equations. So differential, we can define it as a differential about the x and a differential about the y, or we can just integrate them. So area moment of inertia about the x-axis is the integral over all the area y squared dA. All right, so notice this y squared. So distance off, the farther you are off because of the square, the effect of being farther off goes, the square just magnifies that. So the farther the mass is, it really has an effect to jack up the moment of inertia. Now, so here we have y squared dA. So it's distance off of the x-axis, y squared, differential area, add them all up. Relative to IY, it's distance x squared off the y-axis to the given differential area. Now, when we change this to mass moment of inertia, basically the only change is dA becomes dm. We'll be looking at differential mass, and instead of distance y off the x-axis or x off the y-axis, we're going to take a distance r off of the axis we are spinning around. So if we were spinning around here, so this will just become the integral of r squared dm. That's the only difference. So these have a lot of similarities. All right. So moving forward, we can also define a polar moment of inertia for area, which we'll call J0, and that simply is to take to compute the area moment of inertia relative to the origin. So that corresponds to that distance here is simply x squared plus y squared squared. So I said that wrong. This distance would be x squared plus y squared square root, but because of the square that's in the integral, it's just ix plus iy, or it's this distance r from O out to the differential area. So the integral of r squared dA. But r squared is just x squared plus y squared. I'm not going to spend a lot of time with that, but it is an entity that's defined. All right. Now there's one key theorem that whenever you're dealing with moment of inertia, and so there's this theorem exists for both area moment of inertia and mass moment of inertia. We'll look at the area side first. So here I have a blob that's in a lowercase xy coordinate system. And you'll notice there's a little c in here. That's really important. This is the centroid. I realize it doesn't look like it, but don't get hung up on that. This is the centroid relative to the x and y coordinate for this thing. Really should have this piece kind of coming out here so it looks more like the middle. So just tolerate that for the moment. And so here we are at the centroid, and we're going to suppose we know Ix and Iy. Okay? And knowing that, we'd like to find what is the area moment of inertia around another parallel axis. So given I little x, what is I capital X? Or given I little y, what is I capital Y? So that's what we have here. So to compute that, what we're going to do is we're going to compute this I capital X here. And so in doing that, let's just move this up. Start to bring this, let's just stay here this far. So here's the basic definition. The differential amount, now we can just integrate both sides, but relative to capital X, it's the distance from this here up to this differential area. So that'll be a distance dy, and then that distance up here is little y squared dA. So we'll integrate that. We have that there. So here's that. This will be Ix, because we've integrated it. So integrating over all the area, square the distance to get to that point, and we can just multiply that out. Okay. Now, we can now distribute the dA into all of these, so that's going to be our next step. So here I have integral of a y squared dA. Well, what is that? This is little y squared dA. This is just the original I little x. Okay? So we know what that is. Then here I have plus 2 dy, because that's a constant. This distance is a constant from axis to axis. So I can bring that out. I have an integral over the area y dA. And if you look here, I say it's the centroid sort of reasoning that this is 0. What am I getting at? Let me just first comment over here. This dy is a constant, so I can factor that out. So dy squared integral dA, what's that? This is just area. Okay, so integral of dA is going to give us nothing but area. So this is the thing we got to evaluate here. Now, I want you to look at this term. All right, we've seen something like this before. If I wanted to get, for a cross-sectional area, the y-centered, what would I do? I'd evaluate the following integral. Oops, not that one. A. Okay, so this down here would compute the total area. No problem. This is that weighted average in that equation. So let's think. So this would tell us where the YC is. Okay, well, let's just go back up here. Where's the Y center? It's at the origin of this coordinate system. We said C is the centroid of this thing. It's at the Y center, which if you look at that, yeah, kind of looks like that might, doesn't look that far off. The X side of it's really, the picture's bad, but anyway. So this top part, if we were at the centroid, this integral would give a 0. The 0 comes not from the bottom part because the area is non-zero. The 0 comes from the top part. So this is the top part of our centers equation, which by construction we had at the centroid. That means this is a 0. All right. That means that falls out, so we're left with I little x plus dy squared a. So we can go from the, this is the key is this is at the centroid. So Ix, where x goes through the centroid of the object, plus d squared to get to the new axis a. And when we get to doing masses, what's it going to be? It's going to be to move to a new change axis. It'll be d squared to the next axis, m. Very, very similar. All right. So that's what we were just describing right here. Okay. And so to summarize this, we get the following. We can go from this was at the centroid to any other parallel axis. It's simply dy, distance y to get to the new axis, squared times area. Relative to y, we can go from the I little y, which is at the centroid, a distance x squared times a to get to another y-axis. Then we can have the polar moment of inertia, which would have been at the original centroid, plus the distance to the origin of the new axis, squared times a. So we'll just bring this down for a moment. So here was that d, what I just did. To go from JC to JO, it would be the polar inertia at C plus this d squared times the total area. And those are the basic equations for area moment of inertia. Next time out, we're going to start solving some problems. See you then.